I'm Marlene Lockheed, and I'm a member of the Princeton Adult School Board. And one of the pleasures of serving on the board is the opportunity to meet and introduce our distinguished speakers in the lecture series. And tonight's speaker is a special treat for me, as he's both a fellow Californian as well as a fellow Angelino. And he also left Southern California many years ago to come for a short while to the East Coast and has stayed. Daniel Sigmund is a geochemist and an oceanographer. He assures me he did not go into oceanography just for the opportunity to surf in a bunch of really neat places. He studies the global cycles of biologically active elements, in particular nitrogen and carbon. He also investigates the history of these cycles in order to understand the causes of past changes in the atmospheric concentration of carbon dioxide, the role of this greenhouse gas in the waxing and waning of ice ages, and the ocean's response to climate change. He holds a bachelor's in science from Stanford University and a PhD from MIT Woods Hole Oceanographic Joint Program in Oceanography. It's my great pleasure to introduce Princeton University's Dusenberry Professor of Geological and Geophysical Sciences, Professor Daniel Sigmund, who will be speaking on the ocean's role in carbon and climate today and during the last stage. Please join me in welcoming Professor.
So Marlene asked me, is that too loud? No. Okay. Marlene asked me 3 or 4 times whether I had gone into oceanography because of surfing. This is clearly a fantasy of hers. I finally should have just come around and say, yes, that's why I did it. She was much happier. But in any case, I'm really happy to be here today. Marlene has read my title for me, The Ocean's Role in Carbon and Climate, Modern Global Warming and Past Ice Ages. There are 2 basic messages I'm hoping to get across tonight. The first is that the ocean plays a role in the workings of the environment, climate in particular, to a degree that many of us don't recognize. The ocean is to a certain degree out of sight, out of mind, but it plays a dramatically important role. That's why if you look at geosciences departments, environmental sciences departments all over the country, you'll find oceanographers populating these departments and institutions. And the second thing I'd like to get across is that one of our difficulties in terms of grappling with climate and its sensitivity is that we have instrumental data over a very brief period of time. We've been making measurements of temperature for, well, somewhat over 100 years, but not with any great density or robustness. And so, and climate is the long-term evolution of the conditions that we experience. And so we are in a very hard place if we are going to understand climate simply by watching each year roll out in front of us, especially if we have to make policy decisions based on that understanding. And so one of our key opportunities is to use the past as a set of natural experiments, to ask ourselves, to use these natural experiments to study the sensitivities of the Earth, of climate, and then hope to apply those to ongoing changes. Okay, with that, oh yeah, one other point I wanted to make an introduction. You're now going to be plunged into darkness. Okay. This is the hypnotic light level. I feel like I need to make the point that Princeton is a center, both nationally and internationally, in climate science. And this involves my home department, the Department of Geosciences, where we study climate through time. But there are also a number of organizations I'd like to point out. The Atmospheric and Ocean Sciences Program, which is essentially a part of geosciences, but also autonomous, has a great deal of ongoing climate research and work on the carbon cycle. I'm going to in particularly be pointing out the work of Jorge Sarmiento, who's the director of this program. This program has a connection, provides a connection to the Geophysical Fluid Dynamics Laboratory, NOAA's climate model building entity, which houses a great number of climate science experts. And then around campus, we have many people now working on climate and global environment, and the Princeton Environmental Institute provides a mechanism for bringing us together. I hope you're going to get the opportunity to learn about the global environment and climate from more than just me, because this is a great place to learn about it. Okay, so the outline for today's talk. First, I'm going to talk about the current rise in atmospheric CO2 and global warming. This will move us on to recognize the role of the ocean as a sink for both fossil fuel CO2, the CO2 we're emitting to the atmosphere, fossil fuel burning, and global warming heat. This will then turn us to a question, which is how quickly will fossil fuel CO2 and heat be carried into the deep ocean? How quickly can the ocean play this role of a sink for these two things? And we're going to, when having asked that question, we're going to recognize that this largely involves thinking about the high latitude ocean, the polar ocean, the region of the ocean that fills the deep sea and communicates things from the atmosphere into the voluminous deep ocean. Then we're going to move to think about what we know about polar ocean changes over ice age cycles as a way to understand how the polar oceans respond to climate. Okay, that's where we're going. And this is the last part where I'll actually get to say something about my own research. So rising atmospheric CO2 and global warming. The inset figure here, we have years on the x-axis and atmospheric carbon dioxide concentration in the atmosphere on the y-axis as measured at the Mauna Loa Observatory in Hawaii. Some of you will recognize this data set of CO2 measurements as the Keeling curve. Some think of it as the icon of global change. For me, as someone who makes measurements in the environment, this is just an amazing feat of measurement. But what it shows is two things. First of all, you see this up and down, that zigzagging. Each of those is ups and downs is an annual cycle of carbon dioxide in the atmosphere, driven by the growth and decay of the terrestrial biosphere in the northern hemisphere. So that's a seasonal cycle. But then on top of that, you can see there's a year-on-year increase in carbon dioxide concentration. And it continues on. This is now put in the context of a longer record of atmospheric carbon dioxide, going back to 1000 AD here. And this is, the blue diamonds are actually just an annual averaging of the Keeling curve, but the rest of the data are retrieved from the bubbles and ice cores, or the air trapped in firn from ice in Antarctica, which is an amazing way to reconstruct CO2 concentrations back in time. And what it shows is that the Keeling curve is just part of a rapid CO2 rise that began at about 1800. Before then, CO2 was quite stable. We live in what is known as an interglacial period, a relatively warm period. During this part of the interglacial, the CO2 concentrations were stable, and CO2 then started to rise sharply in 1800. I could, but I won't, cover the evidence that this CO2 rise is due to two things, largely fossil fuel burning and secondarily human land use. But this is no longer a matter that we talk much about. We simply know that to be true. Okay. So before I move on to the impacts of the CO2 rise on climate, I want to say a few things more broadly. So the CO2 concentrations, these high CO2 concentrations that we see here, we have to recognize there are a couple of things. CO2 is a substrate for photosynthesis, the substrate by which plants build themselves. And if you think about it, there's not a plant under the open atmosphere on Earth that does not know about the change that humans have caused in the atmosphere. That plant, whether a human has been within 100 miles of it, knows about humans in one sense. That's, to me, I don't know, a dramatic thing. These changes also, these CO2 changes also impact the chemistry of the surface ocean, lowers the pH slightly, and this will affect, probably is affecting, the calcification process of corals and other other organisms that make hard parts. And then a third thing to think about is its effect on climate. And it's the role of CO2 as a greenhouse gas. So let me talk now a little bit about that. This is the simplest possible cartoon I could draw. We're going to be focusing on the simplest possible in this lecture, not because of the audience, but because of the speaker. And so this is the simplest possible cartoon of greenhouse warming and of the greenhouse effect. And so what we have here is the sun, the Earth's surface, and the atmosphere. The sun has nuclear fusion going on in it. This produces heat, heats up the sun, and when an object has a non-zero temperature, it gives off light. And the sun gives off most of its light in the visible range of the electromagnetic spectrum. A portion of that light hits the Earth's surface and heats up the Earth's surface. And so the way that the Earth's surface wants to deal with this incoming radiation, it needs to reach a balance with, it needs to have the same amount of energy leaving as is coming in, otherwise it's just going to get hotter and hotter. It becomes warm enough so that it is now radiating enough light, Earth light, but it happens to be in the infrared, not in the visible, back out to space. Okay? So we have sunlight coming in and the Earth radiating Earth light back out to space. Did I say that right? Sunlight coming into the Earth, Earth light back out to space. Now, this would be the end of the story, but it would also be the end of our story if this was all that mattered, because if you had no atmosphere involved in this, we would have a mean temperature below that of the freezing point of water. There would not be liquid water on the Earth's surface, or very little of it. With the atmosphere, which has a mixture of greenhouse gases in it, a fraction of the outgoing radiation, Earth light, is absorbed by the atmosphere. Now this radiation is radiated both out to space and back down to the surface. And so now the Earth's surface is not just receiving energy from sunlight, it's also receiving energy radiated down onto it from the atmosphere. And so now it's going to have to get even more warm to radiate enough Earth light to reach a balance between incoming and outgoing radiation. Okay, so that is the greenhouse effect in a nutshell. It is not a well, what was I going to say? It's a critical part of how the Earth's climate operates and was before humans came around. And the issue is that raising CO2 is strengthening that greenhouse effect. Okay, so here's some of the evidence that temperature is rising over the last 180 years. And it's impossible to come up with a single smoking gun which connects that temperature rise to the CO2 input. But what is fair to say is that the temperature rise is about what one we would expect for the amplitude of CO2 rise that we've had. All things considered, and there are a number of things to consider. And also, when you take all of the little pieces of evidence together, this is the explanation. The greenhouse effect is the best explanation for this temperature rise. So you would have expected a temperature rise of about this amplitude, you observe a temperature rise of about this amplitude, and it fits all the observations the best. So this seems like the likely explanation. It seems like this temperature rise is likely linked to the CO2 rise. Now this is a problem because CO2 is going to continue to rise in the coming decades and centuries. And this warming in itself is not so much a concern. It's the warming that is possible as CO2 continues to rise, as we double atmospheric CO2 concentrations rather than just increasing CO2 concentrations by a third. We need to understand this world that we're going to be moving to. So now this is where I'm going to transition to focus on the ocean. So what role does the ocean play in the future of atmospheric CO2 concentrations, given that we are going to be continuing to emit fossil fuels in increasing amounts for some time to come? So this is a pretty complicated cartoonish image. It shows all of the major reservoirs of carbon at or near the Earth's surface. And this is a picture, a pre-industrial picture, so before human inputs of CO2 to the atmosphere. Here's the atmosphere up here. You see it's got these clumsy units, 600 petagrams of carbon. That's 600 times 10 to the 15 grams of carbon It's equivalent to gigatons of carbon, if any of you heard that unit. It is actually the smallest carbon reservoir on this picture. There's the surface ocean, with nearly the same amount of carbon. Then the voluminous deep ocean, which has 40,000 petagrams of carbon. And then the terrestrial biosphere, which is something like 3 to 4 times the size of atmospheric CO2. Okay, so, and then geologic reservoirs. I really should point out these. These are tremendously large. And this both includes inorganic forms of carbon, so limestones, for example, and organic carbon. Fossil fuels are a small fraction of that carbon store. And so what we are doing is we are emitting a fraction of this geologic carbon into the atmosphere, something like 6 petagrams of carbon per year from fossil fuel burning. Used to be, we were emitting less than that, now we're emitting more than that. There's also carbon that's being put into the atmosphere from the terrestrial biosphere, from deforestation and land use, agriculture. However, not all of the CO2 that we're putting into the atmosphere is simply sticking around there. Carbon is going back into the terrestrial biosphere, and carbon is also, CO2 is dissolving in the surface ocean. So let's take a more quantitative look at that budget for human-driven carbon, or what I'll call anthropogenic carbon, the combination of fossil fuel-derived carbon and deforestation-derived carbon. So here on the left, we have the carbon sources to the atmosphere associated with humans. We've got fossil fuel emissions of 240 petagrams of carbon over the period 1960 to 2005. And deforestation is about 1/5 of that amount. And then over here we have what happens to that carbon. What you can see here is of this carbon, less than half of it has accumulated in the atmosphere. The rest is already gone somewhere. And more than half of the carbon we put in has already gone to 2 places. One is into the land. And I mentioned this before. Now this is really interesting. Why would the land be taking up carbon? So let's be clear. This is uptake of carbon not associated with this deforestation. Deforestation represents a source of carbon to the atmosphere, but then the land is turning around and taking some of it back up. Now part of this land uptake is deforestation of the past, essentially. We deforested regions, we had agriculture, then we abandoned those agricultural areas, and now they're regrowing organic matter, and that's taking CO2 out of the atmosphere. A second effect, and we don't know how important this one is that if you put more CO2 into the atmosphere, this to some degree fertilizes plant growth, because CO2 is what plants need to photosynthesize. Altogether, we understand this land uptake very poorly, and so it's the results that we've gotten on land, that people have gotten on land uptake are relatively surprising. And there's a lot of research right now, and at Princeton especially, to understand whether this land uptake is going to continue, whether it's going to accelerate, whether it's going to slow down, whether it's going to reverse. We just don't know. Okay. The steady eddy in this is ocean uptake. Okay? This one is around for the long haul. And in fact, this is the eventual fate for essentially all carbon that we put into the atmosphere. Let me explain to you how this goes. So we go back to our world. Do you like the colors for this? I spent a lot of time on the colors. Let's just consider the simple experiment of doubling the amount of carbon that's in the atmosphere just overnight like that. Burn a lot of fossil fuels, I don't know. So we go from 600, in that case we'd go to 1,200 petagrams of carbon in the atmosphere. We go from about 300 ppm in the atmosphere to 600 ppm in the atmosphere. Okay. Well, what's going to happen, starting right away, so it's added 600 petagrams to the atmosphere, is that carbon's going to start to dissolve in surface waters. And then the surface waters are going to mix with deep waters and carry that carbon down into this voluminous deep ocean. And by the time when that's happened, we will have taken 5/6 of the carbon out of the atmosphere and distributed it throughout the ocean-atmosphere system. And since the ocean volume represents most of the capacity, it takes up most of the carbon. There's only 1/6 left in the atmosphere. And in fact, it's better than that. And that's because on the seabed, there is limestone, calcium carbonate. This calcium carbonate derives from plankton that grow in the surface ocean. Calcifying organisms that grow in the surface ocean make little shells. Those shells accumulate on the seabed. And when this CO2 comes into the deep ocean, this CO2 acts as an acid, and it dissolves this limestone, this calcium carbonate, forming bicarbonate. The key thing about this reaction is it consumes CO2. And when that process is done, this buffering of the added CO2 by the limestone in the bottom of the ocean, the carbon that's left in the atmosphere is 30 petagrams of carbon out of that 600 that we put in. Okay? So essentially all of it's been absorbed into the ocean. Okay, so the ocean is not only important for carbon, it's also important for heat. So let's talk about that. So this is an amazing figure. If we were to look at the temperature change that's occurred since the 1950s, since the warming that's occurred since the 1950s, in degrees Celsius, the greatest temperature change has been in the atmosphere. So the atmosphere has warmed more than the ocean has warmed in terms of degrees. However, this plot shows the amount of change associated with the amount of energy added to the Earth's system. So this is the amount of energy that went into warming the atmosphere in this orange box surrounds it here. And this is the amount of energy that went into warming the ocean, a tremendous amount. And what this figure shows is how great the heat capacity of water is. And the ocean is, yes, filled with water. And so it is an incredible sink for heat. And so the way this is working is the atmosphere is warming up because of this added greenhouse gas. And the ocean wants to come along with the atmosphere. It wants to be at steady state with the atmosphere. And so it is taking up heat to reach that new higher temperature. But it has to take up a lot of heat to reach that higher temperature. And so it's slowing the system down. It's the elephant being dragged along. And so this thermal inertia, as we refer to it, associated with the oceans over the top there, has delayed something like 30% of the heating. So this is one of the reasons you'll hear people say, well, even if we stopped emitting carbon dioxide tomorrow and kept it at a constant level, there would still be some temperature rise. It's because the ocean is going to continue to warm to try to reach that new steady state temperature. So you can think of this as good news or bad news. There would be more warming if it weren't for the ocean, is sort of the end of the story there. So the ocean is also a huge sink for heat, and it is slowing down the warming. So what's the problem? This looks great, right? The ocean has saved our bacon. Well, we just wish it would do it faster, okay? So that's what I'm going to talk about next. Okay, this is not the simplest possible figure, I promise you. So, so Antarctica is right in the middle here, and these are depth sections through the ocean. Essentially, so slabs, imagine just slicing the ocean vertically and taking a look at some parameter. And so we've got depth on this axis here. And this is going north into the Atlantic here, north into the Pacific there, and north into the Indian Ocean there. Okay? I hope that's clear. And then there's something that's colored here, this orange to yellow. And the scale is shown here. It has this little thing, sea ant. What is this? This is a calculation from data of the amount of fossil fuel carbon in the ocean. Okay? So how much carbon from fossil fuel burning has gone into the atmosphere, that was in the atmosphere, has dissolved into the ocean. The key message that I'd like you to get from this figure is that almost all of that carbon uptake is still currently in the surface ocean. Okay? Very little of it has made its way down into the deep ocean. And it's really the deep ocean that represents the big capacity for carbon storage. So in essence, we're waiting for this signal, the anthropogenic carbon, to get homogenized down into the deep sea, and also to start reacting with that calcium carbonate that's on the seabed. The places where this carbon is starting to penetrate into the deep sea, I think you can see here in the North Atlantic, there's something called North Atlantic deep water. I'm going to mention a little bit more later. Its surface waters get cold and dense enough to form deep water and sink down here. And I think you can see that they're sort of pulling down anthropogenic carbon along with it into the deep ocean. Is that more clear now? it turns out, you can't see it at all, this is also an important route. A lot of what we refer to as deep water formation or polar ocean overturning or deep ocean ventilation, all of these things mean the same thing, communication between surface waters and deep waters that carries the signal of the atmosphere into the interior. And so this also happens in an important degree around Antarctica. You can't really see any evidence for anthropogenic CO2 making it down into the deep Antarctic yet. And part of that, well, we don't exactly know what this is, but one of the issues is there's so much water around here, you bring down this anthropogenic carbon and it's now diluted with so much deep water you don't even see its signal. Whereas the North Atlantic is a pretty small basin, so you can see the buildup of anthropogenic carbon. Anyway, we think it's happening there too. Okay, this process is happening slowly, and the thing is that the rate of this process can change greatly. We know that this overturning involves the temperature of the surface and salinity of the surface relative to conditions in the deep ocean, and that is very sensitive to what atmospheric conditions above are. And so one of our big concerns going forward is how will the polar ocean overturning change as climate changes, because that will control how quickly anthropogenic carbon can get into the deep sea to go away, and how much the ocean can slow down the warming while we still have anthropogenic carbon in the atmosphere. It turns out that this question of how the polar oceans change, will change, do change under climate, is important for more than just global temperature and more than just for carbon sources and sinks. There are two things I want to focus on here. One is poleward heat transport. And what I mean by this is the transport of heat from low latitudes up to high latitudes. And the best example I can give you is for the North Atlantic, which is shown here. These red ribbons show the warm surface circulation of the North Atlantic, part of which branches up into the high latitude North Atlantic is the North Atlantic Drift. This water is already salty, but it's warm. But in this region, it cools down. It releases its heat to the atmosphere, cools down, and now it's both salty and cold, and that makes it dense enough to sink, thus the North Atlantic deep water formation that we talked about before. And in the process, of course, it's releasing heat to the atmosphere. And so this process of polar ocean overturning is delivering heat to the Northern Hemisphere, the high latitude Northern Hemisphere, especially Eurasia. Similarly, because of this North Atlantic drift, there's warm water on this side of the Atlantic, and that allows winds from the south to pass somewhat northward in the weather patterns and provide additional heat to the high latitudes. If this were to shut down, if this overturning were to shut down, for both of those reasons, we would have cooling. We would expect that to push the system. I should be careful what I say. This will lead to, in a global warming world, less warming in this region, more warming somewhere else where that heat's no longer coming from. But also big changes in global wind and rainfall patterns. Okay. A second reason to worry about wonder about how the polar oceans will respond to climate involves ocean productivity. So there are two beautiful maps here. You have to admit it. This is a map of surface ocean chlorophyll concentrations. Chlorophyll is the pigment that is used in photosynthesis, and so this is a rough metric of where algae are growing in the global ocean and their abundance. And the panel below is of surface nutrients, in particular, my favorite surface nutrient, nitrate, or my favorite nutrient, nitrate, which is a nitrogen nutrient. And so where, I should have said, where the blues are here, that's low, and it goes from green to yellow, that's higher, and the same for nitrate. And so the key message here is you see that the polar regions in the Southern Ocean here around Antarctica and the North Pacific and in the North Atlantic have relatively high productivity, high algal biomass. And this is a direct result of the fact that in the polar regions, because surface waters are cooled by the atmosphere and by a lack of solar insolation, the surface waters tend to be cold enough to be dense enough to mix down into the deep ocean. Cold water is more dense. Okay? And so in these regions, because of the polar ocean overturning, you're bringing up nutrients from the deep ocean into the surface layer, and that fuels productivity. Okay? So if you change these polar processes, this exchange between the surface and the deep in these polar regions, you're going to be messing with you're going to change the ecosystem structure that, for example, is the base, the food source for the fisheries that we take advantage of. And you're also going to have consequences for things like large marine mammals. So these are just some additional reasons that one wonders about how the polar oceans respond to climate. Okay, so well, how will the polar oceans respond to climate change? This has been addressed in the context of global climate models. And what I'm going to do now is show you the most common result that's come from those models over the last 20 years, I guess, of these types of model experiments. This particular result is from the Geophysical Fluid Dynamics Laboratory here at Princeton. So there are two experiments that are being conducted here. One is a control, and I'm not going to say anything more about that. And then the other is a warming experiment. Basically, the model is being imposed on this global model of the atmosphere and the ocean is the rise in CO2 that is currently occurring, along with other factors. This is leading to atmospheric warming and surface ocean warming. And the result, and it shows something here that's important for the polar oceans. And so what is plotted on this axis here, so this is years on this axis, what's plotted here is the vertical density gradient, so the density difference between surface waters and deep waters in the high latitude regions. And what you can see is that in the warming experiment, this density gradient becomes stronger, which is to say that the polar oceans essentially stratify as warming proceeds. And there are two things that are driving this response. One is transient, in the sense you're warming the surface because of global warming, but that hasn't communicated itself all the way to the deep. So now you have warmer water over you've warmed the surface but not the deep, and that leads to a stronger density difference. You've made the surface less dense while you haven't changed the density of the deep. And that makes the surface more density stratified. It makes it harder for the ocean to mix vertically. Okay? And then, in addition, in the warming experiment, you supercharge the hydrological cycle. It's now evaporating more at low latitudes, raining or snowing more at high latitudes. And that deposits fresh water on the high latitudes. Fresh water is less dense than salty water, and so that is a secondary cause for this increase in density stratification. So this is what the models give. It makes good sense that they give this, just in terms of that wonderful explanation I just gave for you, right? Okay. So clearly it must be right. Okay, so this is just to wrap that up. Polar ocean stratification is predicted under global warming. Tell me that's not my phone. Okay, so now we're going to move on to the part where we've just asked the models how the polar oceans are going to respond to climate. Now let's ask the past. That's what we want to do. And the truth is that we could spend a semester asking that question. I'm just going to give you one little bit. And I'm going to focus on the last ice age as the natural experiment here. So here are some things about the last ice age. So the last ice age was about from 60,000 years ago to about 20,000 years ago. During the last ice age, there was extensive northern hemisphere ice and extended alpine glaciers. This is some kind of cartoon of the ice extent during the peak of the last ice age, known as the last glacial maximum, about 25,000 years ago. There was a very large ice sheet over North America and over the western half of Eurasia here. Sea level was 130 meters lower, and that was dominantly because you'd taken all this water out of the ocean through evaporation and piled it up as ice on land. So there's less water in the ocean. The continents were about 5 degrees C colder, and the place that probably cooled the least, which was the tropical surface ocean, cooled by something like 3 degrees C. So multiply by 9/5, please. Okay, the cooling was not just almost all the ice sheet growth was in the northern hemisphere. Antarctica basically stayed the same size, but the cooling was bipolar, bi-hemispheric. Okay? It was a global phenomenon. There were also huge environmental changes on land. The forested areas, many forested areas were replaced by grassland, open woodland, and steppe. Very different Earth. Shown here is the reconstruction of atmospheric carbon dioxide over the last 25,000 years. Okay? So here, this last little, that's the anthropogenic CO2 increase. Here was the interglacial that we were in. Oh, I have little windows for this. So this was the interglacial we were living in. CO2 levels were about 280 parts per million before we started adding carbon. And during the last ice age, atmospheric CO2 was below 200 parts per million, or about a third lower than its pre-industrial interglacial value. So yeah, there's the last ice age. So CO2 concentrations were lower. Well, that's pretty interesting. So during the last ice age, CO2 concentrations were lower. That begs two questions. First, how important was the lowering of CO2 for the occurrence of the ice age? Right? How important was CO2 in that climate change? And second, what in the world caused CO2 to be lower during ice ages? And these things are somewhat circular, right? But what I want to try to do today is address this second question. Okay? Why was CO2 lower during the last ice age? Or this is really sort of what set us off on this research direction. It's a better way to put it, that question. Okay, so one of the key hypotheses for why CO2 was lower during the last ice age involves something known as the ocean's biological pump. Okay, that's a great term. That's a great term. And so what does that suggest to you? Hopefully it suggests the pumping of carbon. Let me explain how this works. So the ocean's biological pump stores more carbon away from the atmosphere than does the terrestrial biosphere. It just doesn't do it as gooey stuff, as a tree you could hug or something like that. It does it as dissolved CO2 in the deep ocean. And the way that this works is algae grow in the surface ocean. Their remains sink into the deep ocean. Almost all of this is broken down back to its inorganic form, CO2 and inorganic nutrients like nitrate and phosphate. But it's occurring in the deep ocean. And the deep ocean is filled with cold water from the poles, and whereas most of the surface ocean is warmed from the sun, and so there's this thermocline or temperature gradient between the surface and the deep, and this makes for a density gradient, and so this keeps the carbon that sank out in the deep ocean. So the carbon has been pumped out of the atmosphere in the surface ocean with which it equilibrates and into the deep ocean. Now, the thing that the phytoplankton need to grow, besides carbon, are nutrients like nitrate and phosphate. Across most of the ocean, which is the low latitude ocean, there's this strong thermocline prevents deep waters from coming rapidly to the surface. And as a result, the phytoplankton completely consume these nutrients. And so the system is essentially, the biological pump in these systems is operating at maximal efficiency. The only option one really has, and this is where what the first hypothesis was for why CO2 was lower, is that there were the nutrient concentration in the deep ocean. If you raise the nutrient concentration in the deep ocean, that will lead to more carbon being sequestered in the deep ocean by the biological pump. And so that was the first hypothesis. Nutrients in the ocean were higher during the last ice age. That has run into trouble as a hypothesis. But what this cartoon, as important as it was, left out is the polar ocean surface. This cartoon only applies to the low latitude surface ocean. So let me show you, let's go back to this figure to make this point about the polar oceans. So what we just saw from the previous cartoon, what the simplification was that the surface ocean had no nutrients in it. And you can see that that's indeed true for the low latitude ocean. But in the high latitude ocean, nutrient concentrations are high. Okay? And when you look at the map of where productivity is, you can see that the nutrients are not here because the phytoplankton are just slacking off. The algae are there in greater abundance than anywhere else, than in the low latitude ocean. The reason these regions are so high in nutrients, and nutrients are not being completely consumed by the algae, is that they're being so rapidly supplied from the deep ocean by this vertical mixing process, this polar ocean overturning that I keep on saying over and over again. Okay? So the polar ocean, the rapid overturning in these regions leads to rapid nutrient supply from below, and that leads to relatively high productivity in these systems. But let's think more deeply about putting these regions into the cartoon that we were just looking at, how the biological pump works. We'll maybe come back to this later. I apologize for that. Okay, so here's our attempt to put what we just learned about the polar oceans, which is that they're nutrient rich, into our cartoon of the biological pump. So here's another one of these cartoons. This is now the low latitude end of the cartoon. This is down the ocean. This is the surface ocean. This is the deep ocean. This is the high latitude region. The point to be made here is that the thermocline, which separates the low latitude surface from the deep ocean, outcrops at subpolar latitudes. So the deep ocean has relatively rapid contact with the atmosphere, and this allows for this overturning process, this easy mixing between the surface and the deep in the polar regions. When we look at this from a perspective of the carbon cycle and the nutrient cycles, it works this way. We've got deep water that's charged with nutrients and CO2 because of the operation of the low latitude biological pump that put all these nutrients and CO2 down into the deep ocean. They now come up into the polar surface ocean, and they're there for not very long, and phytoplankton only consume a small fraction of the nutrients and the carbon that was brought up, and so much of the nutrient that is brought up goes back down unused into the deep ocean. And that leaves the rest of the carbon that came up to escape to the atmosphere. So because there's incomplete consumption of nutrients by algae in the polar ocean surface, the polar oceans represent a leak in the global ocean's biological pump. The low latitudes are trying to push the CO2 down into the deep ocean. The high latitudes, by virtue of their circulation, are allowing the CO2 to leak back out again. Okay. So then the question becomes, how during the last ice age can we imagine shutting off this polar leak? Because this becomes a way that the biological pump could lower carbon dioxide concentrations during the last ice age. We would have increased the efficiency of the global biological pump if we could shut off that leak. So that's what this cartoon speaks to. The left is basically what you just saw, with nutrients and CO2 coming up, nutrients not being completely consumed and going back down unused, and that allowing the CO2 to leak back to the atmosphere. Then we have two options for stemming that high latitude biological pump leak. One is greater productivity, so a bigger green arrow here, which basically means, okay, you have that same nutrients and CO2 coming up, but now you're just scavenging them all back into productivity and sending it all back down, and so that reduces the CO2 leak to the atmosphere. Now there's nutrient concentrations drop and none goes back down to the interior unused, and so we've essentially, the high latitude become as efficient in the biological pump as the low latitudes. This is a wonderful option, but it just doesn't seem to apply to most of the ocean and most of the polar regions. And the reason is the observation we have over and over again when we study deep sea sediment records from the polar regions is that productivity was, if anything, lower during the last ice age, not higher. Okay. Now, the mechanism that I'm enamored with is C. It's not very dramatic to be enamored with C. But anyway, that's the way it is. So this is the stratification mechanism for stemming the biological pump leak. And the way that this works is now you're not having this communication of deep waters into the polar surface ocean. And that has two consequences, or it's happening much more slowly. The two consequences are that for a given, now the slower rate of nutrients and CO2 being supplied at the surface, even with the same or lower productivity as in the interglacial case, the glacial productivity is able to scavenge all of the CO2 that's brought up, and that reduces the CO2 leak. And then secondarily, you're just reducing the opportunity for this stuff to leak into the atmosphere, the carbon from the deep ocean to leak into the atmosphere, because you've turned off the circulation in essence. Okay, I'm going to try to show you some evidence that supports this guy right down here. Oh, to do this, I need to tell you something about a topic you've probably never encountered in your life. Okay? So I'm going to try to reconstruct nutrient conditions of the Ice Age polar ocean, and I'm going to try to do it using the isotopes of nitrogen. Yeah, I know, and it's 45 minutes into the lecture. Okay. So there are two stable isotopes of nitrogen. This just means that, so here's normal nitrogen, N14, it's most of the nitrogen. N15 just has an extra neutron, which doesn't change its chemistry much, okay? But it changes a little bit. And so it's the rare isotope, that doesn't matter. The N15 to N14 variations that we observe in nature are really small, and so we use this term delta N15. The key thing you need to know is with the N15 to N14 ratio, if something is high, its delta N15 will be high. If it's low, its delta N15 will be negative. Okay? The key process that makes the nitrogen isotopes useful for us here is this one. So phytoplankton, we just talked about it, phytoplankton photosynthesizing, growing, producing biomass that's going to sink into the deep ocean. When they're consuming the nitrate, this nutrient form of nitrogen, they preferentially consume N14 nitrate in that process relative to N15 nitrate, relative to the concentrations that they occur in the water. So they've got this bias toward taking up N14 nitrate. Let's see what consequences this has in the modern ocean. So here's some data from the Antarctic Ocean. This is depth into the water column. All the algae are going to be growing up here in the upper 50 meters or so. This plot here shows nitrate concentration. What you can see here, so nitrate is high in the deep ocean, and then as you come into the surface ocean, in some regions around the Antarctic, nitrate concentrations drop significantly because algae are consuming that nitrate, building biomass. Over here is the N15 to N14 ratio of the nitrate. Okay? And so there's some value in the deep ocean. As you come into the surface, the N15 to N14 ratio of the nitrate rises, associated with the drawdown of that nitrate. So what's going on is plankton are consuming that nitrate, they're preferentially consuming N14 nitrate, and so the residual nitrate becomes progressively enriched in N15. Okay? Let me show you this in a slightly different plot. So on this is the same data. The deep is down here. As we go toward the surface, up in the surface, we're going this direction. But the key thing is, so this is a measure of the nitrate concentration. This is the nitrate delta N15. Consumption by algae takes us this direction on this plot, and as we go this direction, the N15, N14 ratio of the residual nitrate rises. So we're preferentially consuming N14 nitrate, the residual N15, N14, the N15, N14, the residual nitrate rises, and you can see that it's a pretty well-behaved relationship. Okay. Well, this is nitrate in the surface ocean. How can this tell me about the last ice age? The answer is obvious. It's the sediments. But okay, so I like to ask questions that way. So it's a flaw. So one of the main types of phytoplankton that are consuming this nitrate are diatoms. These are amazing phytoplankton that build silica shells. The diatoms are growing on this nitrate. And so as the N15, N14 ratio of the nitrate rises, so too does the N15, N14 ratio of the diatoms, which means that the N15, N14 ratio of this diatom biomass, or the biomass of these phytoplankton, increases with progressive nitrate consumption as nitrate's being drawn down. In addition, there are things living off these phytoplankton, such as foraminifera. These are amoeboid zooplankton. These guys, they might not look tough, but he is. I can show you pictures. It's ridiculous. But in any case, this is a zooplankton living off this, and so it follows the same N15, N14 change as its food source does. And then when we go into the sediments, we find that the shells of both of these guys are left behind in the sediments. So the panel on the right is there are these silica frustules, silica shells of diatoms. On the left is one foraminiferal shell. What we do in my lab is we extract these shells from the sediments, we clean them, and then we measure the N15 to N14 ratio of the organic matter that's trapped within the shell walls, these inorganic. This is made of calcite, this is made of opal. And so that's what we measure. I mean, most people think there's no nitrogen in these things, but we're from Princeton, and there's nitrogen in everything. Okay. So this is what we're making measurements on. And the reason we're not just measuring the bulk organic matter in the sediments is this stuff is continuing to undergo reactions as it sits there in the seabed or in my core repository or wherever. So I want this organic matter that's protected. It tells me about the surface ocean way in the past. Okay, so finally, here are some data that speak to how nutrients changed in the Antarctic, one important polar region. Let's start on the bottom. These two plots are actually from ice cores, not from the sediment record I'm going to be talking about. And this is a reconstruction of Antarctic air temperature. Thousands of years is on this axis, so toward the present goes this way. Here's well, I'll start here. Here's the current interglacial. Here's the last ice age. Here's the previous interglacial, previous warm period. Here's the ice age before that. And here is CO2 reconstructed from ice cores. And what you can see is that, I already showed that CO2 is lower during the last ice age than it is during our interglacial. And indeed, there's a very strong connection with climate where CO2 was higher in the previous interglacial as well and low in the previous glacial. Okay, so very strong coupling between CO2 and climate. That's pretty amazing. Now to the sediment data. So the first thing that I don't want to say much about is this top guy. This indicates, this is a measure of barium in the sediments. And this isn't the best record ever, but there are many records like it from the Antarctic. And they all show that productivity was higher in the interglacials, this peak and this peak, than during the ice ages, here and back here. So this is, I already suggested this, that productivity was lower in the Antarctic during the last ice age. Here's where the nitrogen isotope data come in. Just to make things harder, I plotted the delta N15 scale upside down. So higher delta N15 is down on this plot. I have three things here. I don't have the time to talk about them. Let's just look at the black dye, okay? That's the diatoms, total diatoms. And the way I plotted this here, higher surface nitrate concentration would be up, and so down would be greater nutrient consumption, higher nutrient consumption, okay, be down. And so what do we see what do we get out of these records altogether? I should have shown you. So here in each of the interglacials, the suggestion is that nitrate consumption was lower, less complete. During the last ice age and the previous ice age, nutrients were more completely drawn down by phytoplankton in the Antarctic. Now here's the weird part. Nutrient consumption was greater during the ice ages, but the productivity in the system, as I just was talking about before, appears to have been lower. So lower productivity, and yet the plankton are consuming a greater fraction of the nutrient supply. What this tells you is that the nutrient supply during the last ice age declined. Okay? There was less nutrient supply, so lower productivity was still able to consume a greater fraction of that supply. You put those nutrients come from the deep ocean by this mixing, by this overturning process between surface and deep waters. And so this yields, so the ice age, there was reduced nutrient supplies. This suggests that during the last ice age, this suggests C, right? This suggests during the last ice age, the Antarctic and other polar regions were more strongly stratified. There was less free vertical mixing in them. And this helped to keep CO2 in the deep ocean and in part explains the low CO2 during peak ice ages. Okay, well now let's take stock. And it's about time to take stock, I realize. What I've just shown you is that the sediment records from the Antarctic suggest less surface-to-deep exchange of water in the polar ocean during the last ice age. So if you turn this around, what that suggests is that warming should cause deep ocean ventilation from the high latitudes. That is to say, deep water formation, this mixing process that communicates surface to deep. This process should rise under warming. Okay. Well, what did the model simulations show you that I showed you earlier suggest? What was the sense of change there? In that case, the global warming scenarios caused a decrease in deep ocean ventilation from high latitudes. So the point here is these are in opposite directions. So what does this mean? How do I think about this? Is this just strictly inconsistent? The answer is I don't know. Okay? Here are some options. Some are going to be more wiggly than others. One is that I'm misinterpreting the sedimentary data. That's not very wiggly. That's just kind of bad. But I have to admit to you that we're working with a system that we don't have much experience with. So there's still plenty of ways to go wrong. Say that. Okay. The other possibility is we haven't sampled all of the polar ocean well enough, and so that we're seeing stratification in some regions, but it's a fluke, and I'm thinking this is less and less possible all the time, but it's still possible. Another possibility is we're talking about different time scales here. I'm looking at something that applies to the ocean over thousands of years, right? Whereas the global warming experiments are over decades and over 100 years. Maybe that's the difference. That still seems unlikely to me. It still seems unlikely to me. It's also possible that there's a non-monotonic, what does that mean? That means non-monotonic climate, polar ocean sensitivity. So what that means is you cause a certain amount of warming and you increase overturning, and then you cause more warming and it causes a decrease in overturning. I don't like those kind of curves, right? But we can't rule them out. And then the last possibility, which is me being dangerous, is that there's a dynamic missing in the models that leads to the wrong result. And in fact, I'm being a little two-faced here because this has already started to emerge. We were generating these kind of paleoclimate data and wondering how they were going to fit in with the global warming scenarios. But as work has been going on in the modern Southern Ocean, we've started to realize that there's been a strengthening of the winds over the Southern Ocean over the last 50 years associated with the warming. And this appears to be starting to drive some increased overturning in the Southern Ocean. We don't know if this is going to hold out. We don't know where this is going. But it's just an example of how complex this system is. It's going to take us a long time to figure this out. But the beautiful thing, well, I think, about our possibilities is that we have a rich record of Earth history that can be retrieved. With relatively little work, we can learn how to read it. And then we don't have to wait as climate changes to learn how climate changes. We can develop some sort of fundamental understanding of it and apply that in a predictive way. Okay, so summary. The ocean is the long-term sink for fossil fuel-derived CO2. The added heat from global warming is mostly going into the ocean, which is slowing the warming, both of these things we've talked about. The future of carbon and heat uptake into the deep ocean will depend on the circulation of the polar ocean in particular. And there are conflicting signs regarding how the circulation will change. I'll be back if you ever invite me. So questions, please.
Is there any indication that the carbon dioxide in the deep ocean, because of the pressure and temperature, is in some kind of a different form, polymer or hydrate or something that changes its character?
Yeah, so if you take pure CO2 down into the ocean, liquefied CO2, below, I can't exact, it's at least below 3 kilometers, something like that, you start to form clathrates, basically CO2, water, ice. The CO2 that's coming in from the ocean is way too dilute for that kind of, so the chemistry that is occurring when this CO2 comes down in water naturally is pedestrian. It stays, it's doing the same acid-base chemistry as it does in surface waters, it just was to slightly different degrees. But when you start talking about purposeful pumping of CO2 into the deep ocean, then you start dealing with these things like clathrates, CO2 that stays as a puddle down on the deep sea floor because it's denser than the seawater in which it is. I have to, every time, I always have to go back and revisit how exactly all that stuff operates, but that's the difference. So one of the concerns with direct CO2 release into the deep ocean, besides the fact that it's expensive, is that near the site of the CO2 release, we've talked about how the CO2 lowers the pH of the water. And so locally it will lower the pH a lot. And that is not good for organisms. The thing is that the ocean is huge, and so you sort of imagine that it won't take, that region of impact is going to be kind of small because there's so much lateral mixing, so much mixing in the ocean, and such a large volume. So I've talked to you about how the ocean has this great capacity for CO2 storage. So an obvious thing when one thinks about it is to purposefully try to get it down there and let it work its magic, dissolving calcium carbonate off the seabed and just staying there. But the big pushback has been on this issue, this local issue, right near the release point. And so there's a fair amount of work right now on these kinds of issues that you're talking about. The characteristics of liquid CO2 on the bottom, the formation of clathrates, and all those kinds of processes.
In terms of the carbon balance, right along the lines of this, how does the large storage of methane hydrates work, do you think?
Yeah, scarily, right? So there are methane hydrates stored on continental shelves and continental margins. So this is, the way that this works is there was organic matter that was sedimented along with inorganic sediments on the ocean margins, natural process of sedimentation. That organic matter broke down and produced methane, which is CH4, and it's natural gas, and it's a very strong greenhouse gas. And if it gets oxidized, it turns to CO2. But anyway, so one of there are vast quantities of this stuff on the ocean margins, and they become less stable under warming. And so one worries that as the upper ocean warms, you're going to start to release some of these methane clathrates, right? And you also worry about this in permafrost, where there's not methane clathrates, but there's lots and lots of organic matter that can degrade to methane and then come out. And so the concern is that these can introduce extreme positive feedbacks into the system, where you cause some warming, you release methane, and then that causes a whole lot more warming. It seems too catastrophic to, I'm good at avoiding things that seem too catastrophic. I think that there has been some recent work on this, trying to figure out exactly how much methane clathrate release there will be. I think that what tends to happen is just the methane clathrate front tends to migrate down some, and so the early imaginings of huge releases of, sort of explosive releases of methane clathrate from the margins is unlikely to come true. But we're going to have to keep our eyes on methane. The thing is, we can monitor methane in the atmosphere, so we know what it's doing. Right now, it's taking a very strange. It was increasing rapidly, and now it's curving over. Now, one big difference between methane and CO2 is that methane has a short half-life, residence time in the atmosphere. It's relatively rapidly oxidized to CO2 by hydroxyl, by atmospheric chemistry, basically. So if we make it, nature is more forgiving with methane releases than with CO2 releases. You put methane in, and decades later it can be gone. It'll be CO2 then, but it at least won't be methane, and methane's a more powerful greenhouse gas.
Would it be science fiction to think that you could produce super phytoplankton that could be produced in the polar sea?
Yeah, right. So this is known as iron fertilization, right? And in fact, we think that there are times in the past when dust naturally fertilized regions of the ocean. Dust is an important mechanism of getting iron out to phytoplankton. So you remember how I said I apologized for... So the super phytoplankton question takes us too far down a strange ecological road, but I'm going to give you the next best option, okay? It's this thing here. So you can ask yourself, why are algae not able to consume all these nutrients? And what I told you is, well, the nutrient supply from below is just so rapid. But in fact, these phytoplankton could be growing more rapidly than they are. They're already growing more rapidly than their subtropical cousins, but they still could be growing faster than they are. And if you add iron, so light is certainly an issue in polar waters, but we've learned over the last 2 decades that iron is this critical trace nutrient for phytoplankton in the ocean. The reason that these regions become limited by iron, we think, is that iron comes into the ocean from above, and it's scavenged out relatively easily. So the major nutrients, nitrate and phosphate, they stay dissolved in the deep ocean, and they come up whenever the deep ocean mixes to the surface, which happens in the polar regions. But the water that comes up in the polar oceans doesn't have so much dissolved iron in it. And so these are places that are ripe for limitation by iron. And so people have talked about, and there have been experiments where people have gone out and dumped iron in the ocean, and you see a biological response. And in 1 out of 3 cases, they have the good fortune of actually seeing the organic matter sink into the deep ocean. What happened in other cases is what often happens when you go to sea, which is the weather destroys everything. But the possibility of fertilizing a patch this large, it comes out to be crazy, right? It's just too vast. We have to remember, find Delaware, right? Delaware is the usual, New Jersey too, right? This is a vast region of the global ocean. And so the idea of changing the ability of phytoplankton to consume nutrients by going in and fertilizing any one region underestimates the expanse that we're talking about. It's still being pursued by people. Some crazy and some not so crazy. Sorry.
Yeah, actually my question is not all that different, but did I understand you said there's 1 gigaton or less than 1 gigaton of carbon being sequestered by all these little critters dying? That seems really low.
No, 1 gigaton. No, so...
Oh, I misunderstand.
Yeah, so the amount, I'm not sure when this came up exactly. We might have been talking about 1 gigaton per... So the biological pump, so if you ask, let's go to this cartoon here. Sorry, I'm sure there's a better way to do this. So just looking at the basic figure, we've got the atmosphere with 600 petagrams of carbon, 600 gigatons, the ocean with about 40,000 gigatons. In the steady state, you've got about 5 gigatons per year sinking out as organic matter, 1 sinking out as calcium carbonate. This process naturally, though, is being balanced by the upwelling of CO2-rich water somewhere else, right? If the system were at steady state, CO2 concentrations in the atmosphere were constant. The way this would work is the ocean would have sequestered away in the deep about 2,000 petagrams of carbon. It's sort of icing on the cake of this 38,000. A lot would be there even just based on solubility. But it has excess carbon of at least that amount. And that's just held there. And it's in balance. CO2-rich water upwells to the surface. Phytoplankton strip it out of the nutrients and send it back down again. Is that any more clear?
Yeah, I think so.
Isn't the molten core of the Earth very hot? And what effect does that have? Why isn't it warming the cool, deep ocean?
Yeah.
And what's happening to the overall temperature of the planet?
Right. So how to answer this question? So there is heat coming out of the Earth. There has been for all of geologic time. It's a tiny heat flux relative to the solar insolation that's coming in at the top. This is not to say that the heat flux into the bottom of the ocean is not relevant for ocean circulation. So let me just give you an example of how this would work. Imagine you form deep, very cold, dense water in a polar region. It sinks into the deep ocean, fills the deep ocean. And now more dense water wants to form in that polar region and replace the stuff that's already down there. Well, it can't do that unless there's some mechanism for getting rid of that dense water that's already down there, unless it's going to form to more dense conditions. And it can't do that if it's the same climate. And so there are 2 ways that really dense water in the deep ocean can get buoyant enough to be replaced by new dense water. And those two processes are downward mixing of heat from above. Okay, so you've got a warm surface ocean above, and that heat just mixes, you've got enough mixing that you mix some warmth down, and that makes that water less dense, and that stuff can come in, now the polar waters can come in and replace it. Or geothermal heating can add heat right to the bottom, warm up that water, and provide another mechanism for bringing it above its original buoyancy, making it slightly less dense than it when it came in, and allow this overturning to continue. Okay? So there are people who have suggested that the polar ocean, it's related to the hypothesis that I've already talked to you about, that the polar ocean overturning decreased during the last ice age. And so this is what I tried to show you. But then the limiting factor on how slowly the ocean could overturn as a whole was this geothermal heat source at the bottom, which put in enough heat into the bottom water that it made the bottom water too buoyant and forced new deep water to form. So it provides something like a floor for how much deep water formation, how low deep water formation can get. Okay. I think what I should have stopped with is that the geothermal heat flux is tiny relative to the amount of insulation, the heat coming in from the sun. And that's because the heat from the interior, part of it is old frictional heating from the coalescence of the Earth, but much of it is from radioactive decay, and that's fission. And it's just not, and we've been losing that over Earth history. Fusion is much better, as you guys you'll get a chance to hear.
How is all of this affecting ocean currents and weather over Europe, for example, as far north of where we are, and where do you see stuff?
Right. So I have to admit, this was sort of a part. I did kind of mess up at that part. So I'm grateful to go back to this cartoon here. So let's think about our options here. One of the big fears has been that this overturning would, the deep water formation here would stop or slow down, that North Atlantic deep water formation would stop, and that this is the day after tomorrow scenario, okay? Where deep water formation stops up here, and that reduces the heat transport from here up to there and causes severe cooling. Okay, well, let's face reality here. So we're in a world with global warming driven by greenhouse gases. And so if this overturning did decrease, most likely what it would mean is that warming would occur more slowly here than everywhere else. It's likely I lost where my questioner was. You just stare at there, thank you. And so, when we think about, so if you shut this down, and this has been one concern, the idea is, you have a fair amount of permafrost here that's melting, the hydrological cycle is ramping up, all this is going to increase the delivery of fresh water onto the continents all drain into the Arctic. That would lead to freshening of these waters here, and that would work to reduce North Atlantic deep water formation. And it's linked in with exactly the model simulation that I showed you, where the polar oceans stratify under warming. And that would, in a sense, be shutting this down. And what I'm trying to say, my point here, is that if that happened, this is unlikely to actually reverse the direction of temperature change. It might mollify it in this region, and it might make it more severe in the places that we're giving heat to here, right? We're just changing the redistribution of heat. Okay, so I'll stop there.
We have time for just one or two more questions.
So in a way to follow up on what he's asking, I'm trying to decide, are you giving this a doomsday scenario, or is there some hope?
No, so okay, well, yeah, this is a good thing to address. We're looking at substantial rises in CO2. So that we think are going to have a range of consequences. And I think I have a slide here. And these include things like sea level rise, changes in rainfall patterns, changes in species distributions, global ecosystems that are constantly in flux because they're trying to adapt to the new climate. What I've been showing you is sort of a part of the puzzle you rarely hear anything about, which is that there is sort of a state for the ocean as well. And this state can change in addition. And the thing about changes in the ocean is it will affect how CO2 will rise into the future and how warming will proceed. And so there's nothing in it, in a sense, that is a doomsday scenario, right? So when we're, what is it that I've said that is worse than what is likely at this point? We can count on something like 3 degrees of warming over the next century, I would guess. Sea level rise will be, it's been 20 centimeters over the last century. It's probably going to be something between 30 centimeters and a meter over the coming century. We're currently losing many of our mountain glaciers, especially our low latitude mountain glaciers. Things are changing. There are going to be winners and there are going to be losers in this. It's going to be different and it's going to be constantly changing. That's what we're talking about.
One of your charts toward the end showed about a glacial age of about 60,000 years, and then prior to that, a CO2 level not much different than what it is now, and then another glacial age of about the same period of time. What's the speculation as to what caused the CO2 levels to increase 60,000 years ago that we survived, and what's happening now?
Okay, so yeah, so this is just a part of the CO2 record we have. It now goes back to something like 800,000 years, and it's oscillating. It's staying between 280 parts per million and about 180 parts per million.
Fairly consistent.
Consistently, and over that time period, it hasn't gone above 300 parts per million. It's currently breaking 400 parts per million. It never, during this record, changed as rapidly as it's changing now. And none of this is a surprise. The processes that are causing this CO2 change involve, what I was talking about was one hypothesis for why these changes occur. But they involve processes that take hundreds and thousands of years, whereas fossil fuel burning is happening at just the rate is much greater. And so we are, we are taking it outside of the natural envelope of CO2, not for all time, right? We're going, CO2 concentrations, if we go far back into the geologic past, there are estimates of it being about 1,000 ppm, some estimates of times about 50 million years ago when, you had crocodiles at the poles, when it was about 2,000 ppm. The evidence does suggest that there's a pretty tight coupling between climate and CO2. Coming back to the doomsday question, those Earths were quite productive planets. But we have to remember that we don't do very well with change, right? I'm just going to say that we're just not very good with change, right? And that's really the key issue, right? The tiniest things, a slight change in is not slight, but changes in foreclosure rates have these huge ripple effects through our economy. We work on economies that get small things change and it has big repercussions for us. We don't do well with change, right? Now you're talking about changing the climate of, switching the climate of New Jersey for Georgia. you know, you're talking about substantial temperature changes, and it's going to cause substantial, it's going to affect us. Right? Now, I don't know, you know, if you ask, we're going into a realm that I have absolutely no expertise in, but if you live in abject poverty, or even modest poverty, I can't tell you that global climate change should be on your radar screen, right? I would not make that argument to you.
We should live that.
Yeah, yeah. So, you know, for me, I entered, let me tell you why I'm here, why I work on this stuff. When you ask how an organism works, you ask how an organism works. You don't ask why an organism works. You don't like this? Okay. Darwin explained why an organism. He provided a very simple explanation for why stable biological systems, organisms, exist, which is natural selection. We don't have any similar view of the Earth system. This system has been stable for life over billions of years, basically since it had the opportunity. Yes, there have been extinctions, but they've been, you know, punctuated in events of in between long spans of, and this is for a system which has nutrient cycles, nutrients which are coming in and out of the system with a residence time of thousands of years, not millions or billions of years. So what are the rules in this system? What maintains this kind of stability? What are the feedbacks? How do these feedbacks develop? We're on the specifics now. We're scrambling to develop the tools that will someday allow us to answer that question in a plausible way. So these are the big questions intellectually that I'm after. I don't know where we're going other than that, you know.
I think that's a great